Across the country, there are construction projects, and then there are mega projects. These are operations so large that they don't just build structures, they reshape entire landscapes. From the air, they look like moving cities of machines. On the ground, they operate like military-scale logistics systems. And behind them is years of planning, modeling, and engineering control. This particular project stands among the largest ever completed in the region, not because of a single building, but because of the sheer amount of land transformed. Thousands of acres had to be re-engineered, elevations had to be changed, drainage had to be redesigned, and millions of cubic yards of earth had to be moved with precision, not speed alone. Before the first machine arrived, engineers spent years studying the site. Soil cores were extracted and tested. Terrain models were built using satellite scans and ground surveys. Computer simulations predicted how the land would react under load, after grading, and across future weather cycles. Because when a project reaches this scale, mistakes are not small, they are extremely expensive. The challenge was not just to build something new, but to prepare the land to support it reliably for decades. That meant layered engineering, cut zones, fill zones, compaction zones, each with different material rules and density targets. Once approvals were secured, the transformation began. Heavy equipment fleets rolled in, excavators the size of buildings, trucks carrying dozens of tons per load, and precision-guided grading machines. Work zones were mapped like grids, haul routes were optimized, movement cycles were timed. At peak activity, once the site was approved, the next phase looked chaotic to outsiders, but in reality, it was one of the most precisely controlled earth-moving operations ever planned. Because this wasn't just digging, this was terrain redesign. Engineers divided the entire area into zones: cut zones, fill zones, balance zones. Some sections had to be lowered by dozens of feet, others had to be raised and reinforced. The goal wasn't speed, it was balance. Every cubic yard removed from one area had a calculated destination somewhere else on site. Nothing wasted, nothing guessed. Then the hauling began. Convoys of heavy dump trucks started moving in continuous loops, load, haul, dump, return again and again. Each cycle was timed, each route optimized. GPS tracking systems monitored machine movement in real time so bottlenecks could be eliminated instantly. At peak production, thousands of tons of material were being relocated every single hour. But moving dirt is the easy part. Making it stay stable, that's where engineering takes over. Every fill layer was placed in controlled thickness. Moisture levels were adjusted. Then came compaction, massive rollers compressing each layer until it met density targets. Field labs on site tested soil strength daily. If a section failed, it was rebuilt immediately. Weather became the silent enemy. Too dry, compaction fails. Too wet, soil weakens. Too cold, material behavior changes. So teams monitored ground conditions constantly. Work sequences were adjusted based on forecast windows. Sometimes entire zones were paused, while others accelerated, just to maintain engineering quality. And while machines moved outside, design teams kept updating models inside. Drone scans and elevation surveys were fed back into simulation software. The digital terrain model evolved every week. This wasn't construction reacting to land, this was construction controlling land. By the end of this phase, the original landscape was almost unrecognizable, and yet no buildings had even started. Because next comes the structural foundation phase, where mistakes become permanent. By now, the ground had been completely reshaped. Millions of tons moved, elevations corrected, soil stabilized. From above, it looked finished. But in reality, the most unforgiving phase was just beginning. Because once structural work starts, mistakes can't be hidden underground anymore. They become permanent and extremely expensive.
This stage is where mega projects separate from normal construction. Every major zone was resurveyed using laser scanning and drone mapping. Engineers compared real terrain data against digital design models, down to centimeter tolerances. If any section was even slightly outside spec, it was corrected before moving forward. Then came the foundation systems. Different areas required different solutions. Some zones used deep load-bearing layers. Others needed reinforced base platforms. In high-stress sections, multi-layer structural beds were built using engineered aggregate and stabilized material mixes. Think of it like building a giant shock absorber under the future structure. Next came heavy base construction. Thick structural layers designed to distribute load, control settlement, and handle long-term stress cycles. Placement wasn't continuous, it was staged. Build, test, approve, then continue. Quality control teams were everywhere. Mobile labs tested density, moisture, and strength samples daily. Survey crews checked alignment and elevation repeatedly. Sensors were embedded in key zones to monitor movement and pressure behavior over time. Nothing moved forward without verification. And then came the logistics challenge no one talks about: coordination overload. At peak build phase, hundreds of machines and crews were operating at the same time. If one sequence ran early, it could block another. If one ran late, it could stall dozens more. So operations were scheduled like air traffic control, with timed windows, access corridors, and priority paths. This wasn't just construction anymore. It was choreography. Every movement planned, every layer verified, every step recorded. Because what gets built next will sit on top of this for decades. And if the base is wrong, everything above it pays the price. Up next, vertical systems, heavy structures, and the most complex installation phase of the entire project. Up to this point, most of the work was invisible from a distance. Soil, layers, compaction, foundations. Critical, but not dramatic. Now that changes, because this is where the project finally starts rising and complexity multiplies fast. Heavy structural systems begin moving into place. Massive components arrive in segments, transported under escort, lifted by cranes that can handle hundreds of tons in a single pick. Each lift is planned in advance. Wind speed limits are defined. Timing windows are calculated. One wrong move here doesn't cause delay, it causes danger. Nothing is lifted without simulation first. Before major installs, teams run digital lift models, testing balance, swing radius, clearance, and load stress. Only after virtual approval does the real lift begin. On execution day, communication is tight, zones are cleared, and movements are slow and deliberate. But structure is only half the story. At the same time, system infrastructure starts going in: power networks, drainage systems, communications lines, control wiring, and monitoring sensors. Miles of cable, miles of pipe, routed through protected corridors and layered pathways, so maintenance is possible years later. This phase feels like organized overload. Multiple trades working in parallel: mechanical teams, electrical crews, control specialists, survey verification teams, safety supervisors. Everyone sharing the same footprint without interfering with each other. So sequencing becomes everything. Install too early, it gets damaged by later work. Install too late, it delays commissioning. That's why mega projects run on dependency chains, task after task linked like dominoes. Break one and the schedule ripples. Then comes integration testing even before final completion. Partial systems are powered up, checked, calibrated, and shut down again. Problems found now are cheap. Problems found later are not. From the outside, it looks like rapid progress. From the inside, it's controlled pressure. Because the next phase won't ask, was it built? It will ask, does it work perfectly? And that question is answered only in the final stage. After years of planning, millions of tons moved, and thousands of coordinated operations, the project reaches its most important phase, testing. Because in mega construction, finishing the build is not the finish line, proving performance is. Every major system now goes through stress checks and live validation. Power networks are switched to backup and back again. Load systems are tested above normal limits. Drainage is tested with controlled flow. Sensors are checked against real measurements, not just design models. This is where hidden weaknesses appear, if they exist. Special inspection teams walk the site section by section. They don't look for what's impressive, they look for what's wrong. Alignment drift, micro-settlement, tolerance deviation, signal delay. Anything outside spec is flagged and fixed. Then come the live simulations. Full-scale operational scenarios are run as if the site were already active. Emergency responses are rehearsed. Failure protocols are triggered on purpose. Teams measure response time, system reaction, and recovery speed. Because reliability is not assumed, it's demonstrated. Regulatory authorities review the data. Engineering auditors verify compliance. Safety certifications are granted only after layered approval, not single sign-off. And then, something rare happens. The machines leave. After years of constant motion, noise, and heavy activity, the site becomes quiet, clean, structured, operational. What once looked like raw terrain is now precision infrastructure. From above, it looks effortless, but every line, every level, every system represents calculation, coordination, and control. Mega projects don't succeed because of machines alone. They succeed because thousands of decisions were made correctly, in the right order, under pressure. What you see at the end is not just construction, it's engineered transformation.